when I talk in my institute, I talk to my atmosphere guys, and then I realized that their concept of a terrestrial planet is not the same as my concept of a terrestrial planet. So we needed to get together and agree amongst ourselves what we call a terrestrial planet. Just to outline that, to the atmosphere scientist, it is a planet with an Earth-like atmosphere. So Venus, Mars, and Mercury would not qualify, for an atmosphere scientist to be a Earth-like planet. Or they say Earth-like more than terrestrial, but Titan may. Titan has an atmosphere that is, from the chemistry, kind of similar, to the Earth atmosphere with the nitrogen in it and so forth. I think Titan is significantly different from the Earth otherwise, but that's interesting to note. The geoscientists, to which I count myself, it is a planet composed mostly of rock and iron. So you have an iron core, you have a rocky mantle, you have the crust, and all the geology on it and so forth. So Venus, Mars, and Mercury certainly qualify. But what about the Moon and Io and Ganymede? These are not planets according to the IAU definition, which is another complication in there because they're not planets. I don't think we need to spend much time in going into the definition of what a planet is. Actually, you can pick that up from the web and just decide for yourself whether you find that agreeable or not. I mean, there are people that have problems with it and others with not. To me, I mean, what is important for what we're discussing here is that these are almost entirely rocky, and iron bodies. So they are composed of a iron core and a rocky mantle, and this is the physics what we're looking at. And they may have an ice layer on top of it. So that's fine. The ice layer is okay, or the ocean or whatever. But and therefore we discriminate that from the gaseous planets that are have that gaseous envelope. Actually, just to pick up on that, Francis, there isn't. I mean, I was speaking about the giant planets having these big cores, from the point of view of those who do the accretion modeling. But if you come from another perspective, if you look at it from modeling the geophysical properties or the physical properties of these planets, you're not required to give them a big rocky rock iron core. You can actually model Jupiter entirely, that's extreme, but entirely without a rocky core. So it is not clear, that that Jupiter has a 10 Earth mass core. It's not entirely clear. I mean, the data do not require that. I mean, you can form it by having this big core and collapsing the gas on it. But maybe in 10 years' time, some clever guy someone amongst you, comes up with a model to build a Jupiter without that. I don't know, but from the perspective of the interior modeling, it is not required to have a substantial rock face in these things. Now, Francis may argue from a cosmochemical point otherwise, but I'm just putting it from the angle of the physics of these bodies. Okay, so the exoplanets have provided us with a new samples of planets and planetary systems. Most of this discovered rocky objects to date, fall in this class, super Earth and mega Earth. And that, of course, is a bias, that comes from the observations. I mean, that doesn't say that, other planetary systems have nothing, rocky other than super Earth and mega Earth. There may be smaller planets in there, but it is just a bias in our detection capabilities. I mean, there have been claims now to having discovered, I think there's still candidates of that are Mars-sized, down to Mars size, But that need to be confirmed and so forth and so forth. Okay. What are we doing with these terrestrial planets? I mean, you know, people like myself and others, you know, they try to understand them from they apply a theory from a physical point of view. And I have to say that this is mostly thermodynamics, what you're doing with them. You know? So you look at the interior structure, you know, try to understand, you know, whether they have an iron-rich core, rocky mantle crust, phase transitions, chemical layerings, and the variations with steps of thermodynamic and transport variables. So, you know, thermodynamics, transport theory, you know, this is the kind of stuff that you're using to study these things. Then interior dynamics, core and mantle convection, heat transfer, volcanism, that's the expression on the surface or near surface, tectonism or tectonics better, magnetic field generation. You know, this of course brings in you know, the electrohydromagnetic parts, rotation and tides, tidal dissipation, but also, you know, if you look at the atmosphere, then seasons, evolution from the accretion to differentiation, core formation, outgassing, and then cooling, and, you know, by cooling, then providing work, deformational work, you know, that then gets you the topography and all the nice geology that you can look at. And then, of course, habitability and life, and the question, is there a feedback to planetary evolution? Now, important elements of the theory are thermodynamic properties. So when you model planets, I mean, you usually are concerned with looking at density, or the thermodynamicists would say specific volume, but that's the same thing. Temperature, pressure, the composition, and how the composition affects then, for instance, transport variables. Chemical reactions can be of importance, although geophysicists often, you know, leave them to the geochemists, and you know, that's often done. Phase transformations. Then we have energy sources that power the machine. Accretion, so there is, when you form the planet, there is energy deposited in it. I mean, if you start out with a small thing and then you rain stuff on it, then the kinetic energy that is turned into potential energy is dissipated as heat, you know, on the planet, and you heat it. Radioactive decay is a very important element. We've already seen aluminum 26 at work. We're not really looked at iron 60, but these are soon gone, and the planet is left with these guys here, uranium, thorium, and potassium, to heat it. And one of the big debates, you know, that is still ongoing, I think, is just how much of it is powering the energy balance of the Earth and other planets. I mean, is it like in the old days, in the very old days, you know, people believed that the heat flow out of the Earth was in equilibrium with the radioactive decay, and that you could calculate the concentration of radioactive elements by looking at the contributions per unit mass, and then balance that with the heat flux out of the Earth. And here you have your radioactive heating rate. But we've learned in the 80s, I think, it was that cooling, you know, was an important contribution to the energy balance, and that you know, the radioactive decay could not balance the heat flow entirely, and just how much of it is still a matter of debate. Transport properties, viscosity, we will you know, encounter the temperature and pressure and volatile dependent viscosity a few times during the remainder of this talk. It's basically the most important quantity, you know, that sort of determines, you know, how a terrestrial planet evolves is the viscosity of the mantle and to a lesser extent the viscosity of the core. Thermal conductivity, porosity may matter, although not in the bigger things. That is you know, if you look at small planetesimals and small bodies in the asteroid belt, for instance, that would not qualify actually as a planetary body. Porosity may matter. It also matters, you know, in near surface layers, for instance, the regolith of the moon or in Mars, but not in the deeper interior. Electric conductivity is an important element, you know, that needs to be considered. Now, the basic understanding of at least people like myself have of a planet is that we look at it as a heat engine. What it basically does is it converts thermal energy into gravitational, deformational, and magnetic field energy. So, you know, when convection, you know, brings material, you know, up, you know, you can in-place it, and when it then cools, it has a potential energy surplus with respect to its surroundings. You can deform a mountain belt, you know, and form the Alps, you know, and perform deformational work, or you form Olympus Mons on Mars, for instance, and you produce a magnetic field. But the observation is that this engine is an integral part of a more complex system, and I try to outline this here on the side to the right. So when we look at near-surface processes, we have the Earth's crust, we have the atmosphere, and there is interaction between the atmosphere and the crust, I mean, through and the hydrosphere through erosion, for instance, and similar processes. There is an effect, a clear effect of the biosphere in this circle, because the biosphere is working at the evolution of the atmosphere, and also, you know, has its effect on the hydrosphere and on the crust. So that circle is, you know, relatively clearly understood in a way. But then we go deeper and we put the mantle into there. And then we have the volcanism feeding the crust, the evolution of the crust. We also have the mantle degassing and feeding the atmosphere. It may be the most important process in forming the secondary atmosphere after the first, you know, accretionary atmosphere is gone. So there is this interaction. But then, you know, if you have plate tectonics, and this is this thing down here, and I assume that, you know, you all have at least heard about plate tectonics before, but still, let me just say that with plate tectonics, you form at so-called mid-oceanic ridges, you form new crust, you move it to the side by the pressure that is exerted on it, on the formation, on the drag that is exerted by the flow of the mantle, the convection of the mantle underneath. You move it until the plate collapses and it sinks into the interior. And then deep in the interior, you close the circle, and then you know, have this machine going on. And this machine, this is basically the machine that you know, creates the volcanism that pushes you know, parts of the crust to the side, and, you know, is at the heart of folding up mountains. That drags water into it, you know, that is in the hydrosphere, and that creates new continental material at subduction zones and so forth. So the closing of this circle between the crust and the mantle is an important element of the tectonics of the Earth and the working of the Earth. Now on Mars, we believe that this is not closed. So on Mars, you don't have that. On Mars, there is a plate that is on top of it. There is volcanic activity, you know, or has been, or has, yeah, volcanic activity for some time, Olympus Mons here, and you may put some volcanic load on it and then maybe erode the crust from underneath, but you do not have that efficient cycling that you have here, stuff that comes up, takes stuff from these other reservoirs and brings them back in, and closes this cycle here. So that is the element of plate tectonics. Now, plate tectonics is an interesting thing. I mean, plate tectonics is in a way similar to terrestrial planet, depending on who you talk to. I mean, if you talk to somebody who's making his living from being a tectonics expert, he will say that plate tectonics has certain things that are required. For instance, the stiffness of this plate, that this plate moves laterally in a stiff fashion, or other things. I'm not an expert in that, but I won't go into much detail. Or for the geologist, the rock suit that defines these margins is an important element of that. For the theoretical planetary geophysicist, it's not that important that this thing is a plate. I mean, the important thing is that you bring this stuff into the interior and move things about. So from theoretical planetary geophysicists also know what they call mobile lid convection. So this is a mobile lid, and on the mobile lid we don't have any requirements on being stiff or something like that. We only have the requirement that we're moving things about, and so in a way, I mean, that would suffice our requirements, at least from this perspective. There may be other perspectives where it becomes important again, but from the perspective of this talk, I mean, I wouldn't really care whether you, have it as a plate or a mobile lid or whatever. Anyway, so that is what I wanted to say about that. Now, this putting down this cold stuff in here is like stirring your pot on your surface. I mean, on your oven. And what it does is it enhances convective cooling. And I will show you later an image where you see that you are moving you're operating your convective cooling between a higher temperature as in other competing models. So you temperature difference. So you have this cold stuff that is put in here. And now the increased conductive cooling cools the core here. And when you cool the core, you drive the dynamo that generates the magnetic field in there. Maybe, no, this is not. And the dynamo action then creates a magnetosphere that at least shields the whole thing from part of the, the not the nice things that come with the solar wind. But then, of course, you have, you have other things here that of course, endangers this system. So the whole thing is an intricate system that needs attention, and I'm not sure that anybody has come up with the whole description of it, but parts of it are then, of course, subject of studies and theoretical modeling. Now, I said that we're interested also in the other the other terrestrial-like planets around other solar systems. And here's just a quick summary of what we know. We know that mostly we know the Jupiter-like planets. I mean, there are some Uranus and Neptune-like planets, and there are a few Earth-like or rocky planets that that we know and that we have mass and radius of, so that we can actually tell it has the density of something that needs to be explained by rock and iron. And here is a chart that has density, and that's why they are there, because they have been observed both in the radial velocity method as well as in the transit method and the mass. And here is a collection of planets, and you see that there is, I mean, usually what we're having in the exoplanet community is a disjunct set of values. I mean, you have the blue ones that are the radial velocity method detections, and then the transit detections. And we don't care too much about, you know, what is plotted here. I mean, it's the magnitude of you know, the star which they orbit. But to note that they are disjunct. And what we actually would like to have is that, because with the radial velocity method, you're getting the mass. And with the transit method, you're getting the radius. And we would like them to coincide such that we have a lot of planets from which we know both the mass and the radius, and therefore the density, and therefore the chemistry. And this is something that actually the Plato mission will do. I mean, Plato will detect and observe planets in that regime, there where the radial velocity, you know, planets are, and thereby give us thousands of planets that we would then have a mass and a radius, so we can do some geophysics or planetary physics with them. So what are people like myself, why are we interested in exoplanets? I mean, given the fact that up to now we don't have too much information about them. Well, you know, this is a paper by Latham et al., who's been looking at the chances, I have to say chances of small planets. So there seem to be a lot, so hopefully that is true. But what's also interesting is that you know, the systems themselves, and I alluded to that during my talk a lot of the times, that we find systems where the giant planets are much closer than Mercury in our system, and we were wondering about the habitability of these systems. And we also are puzzled, you know, by this thing here, that the orbital eccentricities vary so much, as well as, I think, the inclinations. So that is something that is puzzling, because in our solar system, we're basically down here. We have very small eccentricities and very regular orbits, you know. And you know, if the eccentricity varies as in these other systems, there is the chance for dynamical instabilities. You know, in the previous half of my talk, you know, we've seen these instabilities, and they're usually coupled to eccentricity variations. So that can be a problem. Another thing is that we're interested in is this thing here that I took from an old paper by Russell in the 1930s. Which looked at the maximum radius that a planet can actually have, and derived this formula for the critical pressure in the center of it, tied to the molecular number. And what you have is actually that a planet cannot grow to a you know, any size, but there will at some point, you know, it goes into in the Brown trough regime, and then it decreases that. Now, in our solar system, we have Jupiter and Saturn pretty close to this maximum, about somewhere around here. But the terrestrial planets are down here, and it would be, of course, be interesting to get planets that are closer, you know, to this maximum value in other systems. So that's an interest. Here's a paper, here's a chart from Guillot and Gauthier, who's looking at that. You know, for a gaseous planet point of view, and also at hot Jupiters and how their atmosphere interacts with their host star, but we don't have much time to look into that. So, I mean, this is the radius-mass relation that people have come up with to explain exoplanets. You see the large variations of you know, the error bars, I mean, in the radius and mass determinations or estimates. And here is our solar system, and you see that with some of them we're getting, you know, upper here and into interesting regimes. You know, what is it's not in the legend here, but this is a planet that's basically made of ice, and this is a planet that is basically made of iron, and the Rockies are in between. And you see that some of these planets, at least, you know, if you can take their values at face value, that require substantial, you know, water components, you know, to explain their densities. So, I mean, this is this opens up, you know, a whole new set of parameters for the theoretical geophysicist to study. And then there are some that, you know, cannot really explained with these models. So what is happening here is a a Uranus type thing or whatever. Here's another look at this, though. What I'm saying is that terrestrial planets are relatively well understood, although Earth plate tectonics still poses questions. Pressure and compression are relatively low, much smaller than the critical pressure for degenerating into Fermi gas. This is what defines this maximum here. We have the advantage of that the pressure range is largely accessible actually to experiment for the terrestrial planets. I mean, the diamond anvil cells, you can get up to ranges that would correspond to the lower mantle and maybe even core pressures, although I'm not quite certain about that at the moment. So the pressure range is accessible, while the rock rheology is highly nonlinear and complex, I mean, there is still a way that we can actually think that we can handle it and come up with models like Mars. Now, if you compare a super Earth with that, then you would say that the pressure range in the Earth covers only the outer shell of a 10 megaearth super Earth. So if that is the Earth, then the Earth mantle corresponds to this little bit of the outer shell of the super Earth. For instance, the post-perovskite phase that has been much talked about for the lowermost Earth mantle, is not very well studied, but there's a lot of activity going on here. Is pretty close to the surface in a super Earth. There may be more phase transformations that we don't know about, no, this is the post-perovskite phase, I'm sorry, that we don't know about on the Earth that would determine the properties of the deep interior. It is actually not clear, and this is of course something for the chemist, that there's actually an iron core, or whether or not iron and rock may dissolve into each other, and that there is no clear separation between a core and a mantle in a super Earth. That is of course very speculative, but we can think about these things. And also, I mean, this is from a work that Lada Stamenkovic and Doris Breuer and I published a few years ago, where we did models of super Earth and their thermodynamics, we were pointing out how you have to extrapolate. So this is something that is covered by experiment and relatively well understood theory for a terrestrial planet. And this is where you end up in the center of or the core mantle boundary of a 10 Earth mass super Earth at a terapascal, and you see that what we're doing is, I mean, this is amazing, how we extrapolate that, and this is of course very dangerous, if you do these things. So we need a much better understanding of what is going on here, we're at the moment we are formulating a research project, together with guys who do first principle calculations of equations of state, in order to see that we get a better handle on this. But this is a very demanding task. Okay, geophysicists at least try to understand the properties of planets from a very simplistic chemical component model. So we're modeling them by considering a gas component that is consisting of hydrogen and helium. Then we have what we call the ices, although this is not necessarily in a solid form, ammonia, methane, and water. And here you see a ice mantle, so to speak, the ice layer of Ganymede. But this is an ice, this is ice too. I mean, this is Uranus and its gaseous envelope. And then there is the rock iron component. And from the material properties of these, we're then, for instance, making models of the evolution of Ganymede by coupling what we believe about the transit properties of the ice with that of the rock. And then we're looking at how to explain the the magnetic field of Ganymede, just as one idea. I think we can skip that, and this is another super Earth discussion that we don't need for this time. So, but this is an interesting, at least I find this an interesting diagram. And I think it was first put forward by Dave Stevenson, and I call it Dave Stevenson's Toblerone diagram. And it considers these three components, ice, rock, and gas. And it postulates that you can actually, popularize this whole space that is, made up of that. And I don't know if you really can do that, but anyways, what you see is that in our present solar system, you're basically at the edges only of it. So you have the Earth, which is basically a rock thing. You have Jupiter, that is basically a gas planet, and you have the ice moons that are sort of in between. I mean, the ice component, rock, right down here. But in principle, one could think that one could have many more variants of this, and might detect them, in other planetary systems. Okay, now coming back to our solar system, let me just briefly introduce some of the physical properties of the planets in our solar system. So the radius normalized to the Earth, so you see they're all in the same ballpark of sizes between, for the Moon, the smallest, about a third to the Earth, and Io is about as big as the Moon, and Venus is big as the Earth, and so forth. We have a variety of masses. That is, of course, much more larger than that, because that depends on the power of 3 of the radius. Therefore, we have a larger variation here. Interestingly, the density is relatively similar, but even more so when you remove the pressure effect, the compression effect on these densities. And then you find that Venus and Earth are in that ballpark. Mars is not too much away from it. The Moon is lighter. Ganymede, with its large ice component, is much lighter. Io is a bit lighter, but falling in the smaller park of these terrestrial planets. And Mercury, of course, sticks out. Mercury is very dense, and the simple explanation is that Mercury just has a lot of iron, and that is reflected in the size of the iron core that it is associated with, of 0.8. I think that number still holds from the messenger data. While otherwise, a value around of about half of the radius is more common. Now, there is, of course, the exception of the Moon, that has a very small radius. Ganymede, if you take away the ice component, then you would still have about half, and Io is again in this ballpark. So a core radius that is about half the planetary radius seems to be pretty much representative of a rock-iron thing, and if you add a substantial ice component to it, then of course it's about a third, and a third. I should also note, and I will use that later, that there are magnetic properties. So we have the Earth having a Dutch-generated magnetic field. Venus doesn't have one. I mean, there's an upper bound to the magnetic moment. Same for Mars. I mean, it has crustal magnetization. We know that, so it once had a magnetic field. The Moon also once had a magnetic field. Ganymede does have a small one, and Mercury does have a small one. So we have the magnetized bodies, that is today Mercury, Earth, and Ganymede, that we need to explain, and I won't go into Ganymede, I don't have the time for that. And we have those that once had a magnetic field, Moon and Mars. And some of us, including myself, believe that Venus also once had a magnetic field, but we cannot prove that, at least at the present time. A quick look at Mercury and the surfaces of the planets, just to get you acquainted with. Now, this is Mercury. is a basically a battered world. You know, here's the Messenger spacecraft, created, similar way to the Moon, and not much of endogenic tectonic activity that formed the surface. Different from that is Venus. Now, Venus is in so far particular that it has this optically thick, massive atmosphere that does not allow us to look through, with cameras on a spacecraft. So we explore Venus by looking at it with radar. The radar gives us then, the tectonics and the topography and so forth. You may wonder why this is so yellow. I mean, radar is, of course, black and white. Now, NASA, this is a NASA image. NASA has used the color that the Soviet lander had seen, so to speak, in their short lifetimes, of the light on Venus, to use it to color their radar images. Now, there are interesting features on Venus, and that is it is dotted with volcanoes and with lava features that go a long ways, from this volcano here down here into there and into this crater over there. Though there are lava channels that span thousands of kilometers on Venus, suggesting that the viscosity of the lava is actually very low, and that is an interesting thing to consider. Of course, I think that the Venus is very hot, with a surface temperature of about 700 Kelvin. And here finally Mars, with this desert-like planet with an average temperature of, minus 60 degrees centigrade. Major volcanoes, a major carbon system, in a way, I mean, the conditions are not so much removed from habitable, not as much as Venus. And of course, I mean, Mars is our role model of a planet that does not have plate tectonics, as we will look at later. Here is the spacecraft Mars Express, European spacecraft, with our camera on it that produces these stripes, and it's a stereo camera, so we can produce all nice pictures and flies across the surface. We also have rovers on there, so Mars is certainly the planet that has been best explored of all other terrestrial planets or other planets in the solar system, including, I mean, this laser altimeter picture that clearly shows the dichotomy of it with the Tharsis province, a super volcanic province with the carbon that we saw here, those big volcanoes. People have thought that this looks a little bit like a mountain chain on a subduction zone on the Earth, and Norman Sleep has discussed that to some extent, but the consensus today is that Mars does not have plate tectonics, but it has an old surface dotted with craters and a surface that looks much younger, although when you look at the gravity field, you see that the surface here covers with either sediments or lava flows a cratered surface underneath. So there has been some renewal of the surface going on, and this event has sort of flooded this lowland that some postulate could have been an ocean at one time. The atmosphere of Mars is, the pressure is substantially lower than on the Earth. This is the average temperature, high wind speed on it, up to 100 kilometers per second. But let me point to this here. This is the composition of the Martian and the Venusian atmosphere, and you see they are dominated by CO2. While for the Earth we have nitrogen and oxygen. And I can't go into much detail, but I mean, this is usually said, this is the action of the biosphere. So we started out on the Earth with something like that, and we ended up here, and this is because life is on the Earth. living things like you and I, they are relying on this here, and the free oxygen in it that has formed some time ago on the planet and allowed the evolution of the eukaryotes to what we are today. Okay, we've looked at the phase diagram of water before, and here is Mars around the triple point in his Earth. I think we've seen that. I mean, this is the surface again. I mean, this is the desert on Mars, the Venus underneath its yellowish coverage, Mercury and the Earth. Now, just let me point out that the Earth really is peculiar, and here are some of the properties that it has, and that we should be thinking of and need to put into our picture and explain. It's the biggest rocky planet in the solar system. We know the interior structure well. Because seismology, we have seismic topography. We also know the variations of things in there. We have a substantial interior pressure with phase transformations. They should be coming up here, the perovskite phase, the post-perovskite phase. We have a compression up to 30%, and we have an adiabatic temperature rise by 1,000 degrees across the mantle. And we have a big debate on the temperature rise across the core mantle boundary. Now, unfortunately, I don't have time to get into that, but this is one of the hottest topics today in geophysics, to explain, a postulated temperature rise across the boundary between the core and the mantle of 1,000 or maybe even more degrees centigrade. We have active plate tectonics, a vigorously convecting mantle. We have magnetic field. We have an hydrosphere, atmosphere. We have life. Okay, here is the dynamo in the core, and life, and we're back here. Now, one of the important things that we need to understand is interior structure. And here are the constraints that we have on interior structure: the mass, gravity field, rotation parameters, laboratory data, magnetism. But this is for the Earth. We have also seismology and heat flow, but we don't have that for other planets yet. And this is c'est dommage, like I think you would say, because this is the method of getting the interior structure right. Everything up here is fraught with non-uniqueness issues, and therefore we're so much motivated putting seismometers on planets like Mars and so forth. Now, I'm just putting this in, and I won't go into detail because Cyril showed a similar slide. I just wanted to point out that much of these equations are, similar to what you presented this morning. There's a little bit of a difference, in the equation of state. Actually, our equation of state is more complicated, and this is because rock is a complicated stuff. Okay. Now, you have to be aware, and I want to make this morning pretty clear and loud that, whatever people tell you about the interior structure of planets, you have to take that with a grain of salt, because from the, in a way similar to what Cyril did this morning, we have an underdetermined system, have more variables than we have actually constraints, and if we're not having seismology, everything in here you can trade, for instance, the density of the mantle against the density of the core and the radius, and were it not for cosmochemistry that we had, some idea what the mantle density has to be like, we would basically be lost in determining the core size of a planet. And cosmochemistry can help you, and I'll show you a very simple calculation, very, very simplistic, but I learned that from Heinrich Wenke many, many years ago, who's just proposed that. I mean, make the blend of iron and silicate and calculate the mass of the core relative to the mass of the mantle. Just assume that the mantle is made of olivine, the iron of core, and then you have these two ratios here that you can easily pick up from the periodic table. You have, between, I mean, the weights you can pick from the periodic table. You have the iron-silicon ratio from some cosmochemistry, this number here, if that is right, and you multiply that with the ratio that you got here from the periodic table, and you arrive at 1/3 as the ratio between the mass of the core and the mass of the mantle. And you correct that for the mass of the entire planet, and you find that in that case the mass ratio should be about a quarter. And that translates with a density of iron into the famous number of 0.5. So that you see realized, in most of those iron rock bodies. So it's a simple explanation that can be found from here, and all the other more sophisticated models arrive, basically at the same ballpark. Now here is a lander, InSight, that was actually supposed to fly to Mars this spring. That was supposed to do seismology on Mars. Now, unfortunately, the seismometer has a problem, so we have to delay that by 2 years. I'll talk to you then later about that. Now, here is basically what we've already said, that the radii of Venus, Earth, and Mars are about 0.5 for the planetary radius. Mercury and Moon sticking out, and of course that requires explanation. So people are scratching their heads of why is Mercury like this and why is the Moon like that. So the Moon, the explanation lies with its formation as a result of a giant impact. Now Mercury, a simple explanation is that it also had a giant impact that removed much of the rock component and left it with a remainder mantle and the iron core. That's one explanation. Core formation is an important part of the early history of the planet, and is an important way of delivering energy to it, to the interior. Actually, in the early days, we thought that the planets were growing inward out, we start with a small one, you add and add and add and add, and therefore you expected that the temperature would increase towards the surface, because if you crash a thing on a big planet, you dissipate more energy than when you do the same thing with a small planet. And later we then believed that the planet differentiated and formed a core, and thereby reversed the temperature profile. Now that is no longer believed by too many. Now we believe that core formation and accretion occur more or less simultaneously, and that we form the planet actually from at least some, or a large number of pre-differentiated planetesimals, so that core accretion, core formation and accretion go basically hand in hand. I think we've looked at the energy, this is on the energy that contributes to the convection, so we can skip that and go to this one here and discuss a little bit about mantle convection. Now, I already said that it is the essential driver of the planet as a heat engine, and that it drives the surface tectonics and the dynamo and so forth. Now here I'm illustrating the difference between a planet that has just a stagnant lid on top of it. You see this bluish thing. This is a model calculation that we did many years ago for the Moon. And here is your plate tectonics thing. And you see that if you do plate tectonics, you take this stuff and put it down in here. So you take this cold stuff and cycle it with a deep mantle. So you can easily understand, that you are cooling the deep interior much more effectively, rather than when you when you cycle between these temperatures and leave this here untouched, okay, and this is what convection does, underneath a stagnant lid. So that is the difference in the efficiency made visible, so to speak, between plate tectonics and stagnant lid. Let me look at this first. Now you may wonder what is this stagnant lid and plate tectonics or mobile lid tectonics, and this is can be seen from this graph here that is due to Stein and Hansen based on their model calculations. And you see this is convection in a fluid. The viscosity of it is temperature dependent, and now I go back to that slide here and show you this formula. Here is the viscosity, and it's exponentially dependent on the inverse of temperature. So that when you are at cold temperatures, they have very high values, here, cold temperature, high value. You increase your temperature, you go down the viscosity, and you have a layer where the temperature changes relatively little, increase in the viscosity, temperature increases again, decrease of the viscosity. This is the temperature dependence of that. Now you add pressure dependence on that, you sort of iron out some of that variation, but you still are kept with this increase. Now if you do convection calculations with a model like that, you arrive at this here. And you cannot include the cold thing into the flow, which is here. So how do you do that? You do that by introducing, that's one way of doing it, another aspect of rheology, and this is the yield stress. So solid matter may yield to stresses if the stress on it is higher than a yield value. And so if you did a calculation just with temperature-dependent viscosity, and here is the planetary radius, basically, you're down here. You're in this regime. Now, if you add the yield stress to it, make the rheology more complex, then you can go up to you have to make it small, then you go down here and you are in a regime that allows plate tectonics. Now, I'm sorry, I mean this is the stagnant lid with a high yield stress, and if the yield stress is small enough, then you can have this this form of convection. Now, these arrows here indicate that there is a variation of the velocity in this layer here, and it's not plate-like. But to me, for the heat transfer, that doesn't really matter. People have spent much time and effort in understanding how you get this plate-like. Now, this is a good thing to do, of course, no question about it. But for the kind of discussions that we have here on the effects of plate tectonics on the energy balance, I mean, it's not really so much of importance. Now, this is the same thing. Here plate tectonics works with the cold temperature, and stagnant lid works with that temperature difference. Basically the same story. Okay, now how do we actually calculate these models? We have basically two ways of doing so. I mean, the more complete and complicated way is doing finite amplitude convection calculations. And there you solve the hydrodynamic field equations of mass, momentum, energy. And then you put in equations of state, the viscosity and so forth, and you arrive at velocity, temperature, and concentration fields. So this is the full thing, 3D, temperature depends on viscosity over a large range of temperatures. This is the state of the art, so you can't do better. But it is very time consuming. These runs run for days, on computers. So one way out is this thing here. You parameterize the convection flow, and you say that you study from these models here relations between the heat transfer rate of a convecting system and its vigor of convecting. You solve the global energy balance from it, and then you put everything to the side, you add magnetic field generation and so forth and so forth. Now these things here run in minutes on a PC. Yeah? So that these are very much accessible, much more accessible than that here. But you have to have a check on these here through those, and therefore every once in a while you need to do that. And of course, if you are interested in the details, you need to do that. Now here is a full 3D convection calculation for Mars. You see the plumes rising up and things like that. And here on the right-hand side is what you typically get, from a parameterized model. You start with the temperature and you arrive at the present day. Now, what these models illustrate, however, is an interesting thermostat effect that comes from the temperature dependence of the viscosity. It tells you that when you start with a high temperature means low viscosity, means rapid convection, you cool rapidly, and then you come into the transitory regime and come here. Now, if you start that with a low temperature, low convection, heating from the interior, warming up, and then you increase your temperature and also you come in here. And because this energy balance is basically a first-order differential equation, this is the properties of first-order differential equations, and they are like that, and that is why you're getting these. This initial value problem is converging as time goes to infinity, and you go through a value that represents your present planet. And this is actually where you know things. You don't know much of these things here. Now that has caused people, and I also thought about that years ago, that why we're not reversing this? Why don't we start with that here and calculate backward? The problem with that is, and people have done that, the problem with that is that you're going this way. You're missing all these in between. And your solution is diverging, and not converging as you go in that way. Anyway, I mean, this is a hot piece of research, and Jun Kornaga, for instance, has contributed to that and has come up with calculations like that. He's also, and I think that is a very important contribution, looked at how the way to parameterize plate tectonics and how stiffening of the lithosphere through melting and water, would allow different parameterizations, and this is certainly important work that needs to be considered. One outcome of this is that and this is often used, these days in the literature, is that the heat flow classically depended on the vigor of convection to some power of beta. Now, Rayleigh number measures the vigor of convection. It is here's the viscosity is in there. And classically, this is in the order of 0.3. Now, Kornaga has it closer to 0, maybe even negative, which would, in a way, come back to this here, heating up of it. So, maybe one of these days, things can converge. The big difference about this here is that these models, they cannot prescribe actually the ratio between cooling and heating, through radioactive decay, get it as a result. And they typically arrive at what they call the Urey ratio of 0.6, 0.5 or something like that. While cosmochemists, say that it should be 0.3. And 0.3 doesn't work, because, you're getting to, it just is not in this calculation. And if you do it backwards, you arrive at what they call the thermal catastrophe of the mantle, which is a artifact of prescribing the Urey ratio. Anyway, this is an ongoing field of research, and expect things to be evolving here. Now let's talk a little bit about magnetic field generation. There are necessary conditions for the existence of a dynamo. You need an electric conducting field, you need motion in that fluid, electric conducting fluid, motion in the fluid. And you generate the motion, for instance, by cooling and inducing convection, or by freezing of the core and inducing convection. And this is these two dynamos here. There's one dynamo driven by thermal convection in the core. That requires a sufficiently large heat flow from the mantle. So you have to suck heat, from the core in order to allow it to supply enough heat to balance the heat flow across the core mantle boundary, and rather not just conduct it. This depends on the core size and so forth, and you put in numbers, and there are some threshold numbers that you can derive from that. The other more effective way is when you freeze out an inner core, and you have the core being composed of iron and a light alloying component. Now the inner core is then iron, and the light stuff is enriched in the outer core and drives convective flow. And that can be a very efficient dynamo that is not restricted by the Carnot efficiency of a thermal engine, because it's a chemical engine. And this is how it works. I mean, you have a solid inner core made of iron, and assume for the time being that the light component is sulfur. So you crow the core by adding iron to it, and you release the sulfur, and the sulfur mixes and produces convection and powers the dynamo. But you would always be aware of whatever the core does is only the slave of the mantle. So the mantle machine, so to speak, dictates what the core does, and this is the way it is, and not otherwise. Here is a model of Johannes Wicht's that illustrates the flow and the feed lines that can be in a dynamo, and well, this is too complicated. This is a very old paper from '83 that shows the transition of a dynamo from a thermal regime to a regime driven by chemical convection for the Earth, and also says that Venus shouldn't have a magnetic field. And here is the change in the operation mechanism, thermal, and I think I have that illustrated, chemical here. Now, people have looked at that, Laprosse and others, and then you move this transition about closer to today, so forth. But basically, it's the same story. I mean, you are cooling it, you start to freeze out an inner core, and you drive the core convection chemically, and you have an efficient dynamo. Or you can also move it backward, depending on your ideas about the core and the mantle, and how the two interact to cool the core. Mars has this remnant magnetic field, and here is an explanation for it. The critical heat flow for a thermal dynamo. You cool the mantle to begin with, and then you get below this critical value, and you have a magnetic field initially, and you stop it, and you magnetize your crust like here, and then the magnetic field dies. It can resume. I mean, if the core cools further and starts freezing out, it would resume and produce a new magnetic field. Now, the test for that, of course, is the prediction that Mars doesn't have a solid inner core. Now, if missions like InSight would find out that Mars has an inner core, a solid inner core, then we have to start from scratch. Then it doesn't work. And there's something other than that, and there are ways, and okay. Now, in a more systematic fashion, this is how things could evolve. This is the efficiency of mantle cooling, stagnant lid, plate tectonics, light elements in the core. And Doris Breuer has put that together. She puts mercury down here, few light elements in the core, is basically almost iron, stagnant lid convection. And this is early on, and Mars and Venus and the Earth don't have a magnetic field at the time. Now you cool further, the Mercury core is growing, still having a magnetic field. Earth core starts freezing out, produces the magnetic field. Venus is still not catched, and it should have had an early thermal dynamo, but it doesn't have this chemical dynamo, and Mars also. And you know, later, I mean, the Mercury core could possibly be frozen out, depending on the chemistry of the core alloy. Earth would still have be producing a magnetic field, and Mars and Venus may have resumed producing a magnetic field driven by chemical convection. This is maybe how it may go. There's an interesting new development in what is called the iron snow regime from some peculiarities of the phase diagram, but I think we skip that in the interest of time and go to differentiation, which is another element of differentiating a planet is the formation of the crust by melting it. And we've seen that already in this chart where I've looked at the integrated system. That, of course, has fed into the development of Mars and Earth and the differences of that. I also want to go briefly to that to come here, habitability and plate tectonics, and to look at a model that produces some interactions with the two. Now, I also have a discussion of plate tectonics and super-Earth, but we've already spent 1 hour, so we should go across that, and we should also go skip the atmosphere to come at this here. If you want, I mean, can privately later discuss these things, but let me just introduce this here. Now, here is a evolution of the atmosphere as the oxygen, the great oxidation event. I wanted to make the point that is now debated, whether that really is like that, or whether it goes more like that, or whether there is a phase of low oxygen actually. Anyway, and the carbon dioxide decreases, and the methane was active here and decreased. Here is the oxygenic photosynthesis established. And here is the growth of the continents. Now, the growth of the continents has been, sort of linked to this great oxidation event, but not really in a quantitative fashion. And there's something that where the modeling needs to be done. How would you link the burial idea of oxygen to the growth of the continent? This is something that could be done in the future. Now, what I wanted to come to is a discussion of the water cycle and its effect on the mantle tectonic engine and the formation of continental crust. And this is in parallel, of course, to the carbonate silicate cycle, which I would not discuss, to discuss at this point. Though it is very important for regulating the temperature of the atmosphere. Now, though I should note that it has the plate tectonics engine as a element in it, but the water cycle has it as well. And I want to propose a model that I have been looking at together with my student Dennis Höning recently, and this goes a little bit like that. I mean, we have feedback loops between the interior and life and the water and erosion. So we're saying that continental erosion can be enhanced by bioactivity. This is the central part of the biosphere, at least, and its interaction with it. The whole thing can actually also work abiotically, but then the results would be a little different. And this erosion feeds sedimentary basins. So you erode and you feed sedimentary basins that are here. Now, the sediments carry water into the interior. They also block dewatering of the oceanic crust. The oceanic crust also carries water, but the sediments tend to be less permeable than the oceanic crust, and therefore the stuff that sits on the oceanic crust reduces the rate of dewatering the oceanic crust. Now at some depth down here, water is released, then hydrous minerals break down, and this feeds the andesite source region. Let us put it here. I mean, it's about 100 kilometers to 200 kilometers depth. Andesite volcanism provides continental growth and therefore the source for the sedimentation. And the remaining water is injected into the mantle and is part of the mantle water budget. Now water reduces the mantle viscosity by breaking up the silicate chains and enhances the rate of operation of the tectonic engine. And then water is released through the crust and into the atmosphere at mid-oceanic ridges. This is a similar way of doing that, just pointing out here that the minerals get destabilized and water and other fluids are removed and feed the andesite source region. Now there are two feedback loops in here. There's the water loop. So increasing the water influx in the mantle increases the water concentration and the viscosity and the melting temperature, and leads to an increased degassing rate at mid-oceanic ridges. And then there's the continental loop. Increasing the continental growth rate increases the surface of the continents and the length of the subduction zones. And decreasing the length of the subduction zones decreases the continental growth rate. And we find that there is an optimum length of the subduction zones at a 40% coverage of the Earth by continents. And this is actually what you find today. I mean, this is a simple model of putting caps on as continents on the surface, and you calculate the integrated length of subduction zones, and you find that the maximum occurs at a 40% coverage. And this is actually what the Earth does. I mean, believe it or not. And maybe there is something to that, maybe that is a coincidence, but we find that an interesting note. Here is another representation of how these processes are interconnected. So there is erosion through the subduction zones. You put the stuff into the interior, sediments add to it. Then you put the water into it, you produce continents. As the continents grow, you increase the erosion rate and so forth. Now water, you put water into the mantle, decrease the mantle viscosity, the subduction speed. You add water directly through the pipeline to the subduction zone, and you increase the continental growth rate, and some of the water that is degassed from the subduction zone gets into the mantle water budget. So it's all interrelated and works together in a cycle that includes water and the continents. Now the biosphere comes into here through the weathering rate. So we assume, based on literature, that the biosphere acts to increase the weathering rate on continents, and we put that as a parameter in our model. We assume that it is increased by a factor of 1.5, so modest actually. Again, here you put the stuff in the subduction zone. You have water in the sediments in the crust. You dewater, you feed the continental crust production, you feed the mantle with water and put it back and increase the speed of that turnover machine and regulate the growth of continental crust through it. Now, when you set up a stationary system, look for stationary solutions, and you have a phase plane, called the phase plane of continental surface area versus mantle water concentration, you find that there are stable and unstable points. I mean, this is the curve that has the rate of continental surface area being 0. And this is the curve that has the rate of change of the mantle water content 0. And when these intersect, there are stable points, attractors. I mean, the system moves towards them. Now this thing here is stable. A small excursion will always bring you back here. This one is unstable, so a small excursion may bring you to this stable point, or that one, for instance. So there is one at a wet mantle and a high surface coverage, and there's one at a low mantle water concentration and a low surface coverage. And here's our unstable point, and actually that is the Earth. We found that without the parallel combinations, we would actually have the Earth being close to that unstable point. But also see that there is an area around that point where the rates are very small. So this is like a equilibrium, that has like a saddle point somehow, So you're not having too much drive here to move away from it once you are here. Okay, now we've went from doing stationary models to evolution calculations by putting a parameterized mantle convection model in there to calculate, the rate of movement of this tectonic engine. And what we do then is we calculate, for instance, the continental coverage and the mantle water budget. And here you see this is what we predict for the biotic Earth. And we see that it stabilizes the continental surface area. While for the abiotic Earth, you would, with the cooling and the increased continental production, you would overshoot and then try to reduce, the continental surface area to arrive to move basically to that point down here, While the biotic model, is happily settling close to that point here. I have a problem with. And here's the mantle water budget. This illustrates the stuff that I said about these equations. The initial conditions don't matter too much. And also you see a divergence between the biotic world and the abiotic world. And here's the time of the onset of bioactivity that then leads to an increase in the weathering rate in our simplified model, of course. Now here is the evolution in the phase plane. Now these equilibrium curves also move. That makes this thing difficult, because not only does your state variable, there are several paths that we can go depending on the initial value of the mantle water content. This is a wet mantle, a dry mantle. They're all moving, in this way towards this evolving equilibrium point here. And you see how, over time, form these equilibrium points here, here, and here, and how they then again evolve with time. Now, this system basically starts out to go towards here. And then, this thing comes in. So you see that this new equilibrium is sort of coming out, and it gets caught here and stugs and remains, at this point. This is how we interpret this variation. Now here is a few snapshots of the same thing and the abiotic world. And you see that in the abiotic world, we are abiotic. Okay, I should look at abiotic. So it's really straight. Why did because of the same times. I'm sorry. Yeah, abiotic later. We also, and then this equilibrium point goes away. And then the system reverts and moves down to here, and this is why the continents sort of tend to get eroded, basically, and shrink. It's an interesting idea maybe for geologists that continents may shrink, but anyway. Now, this is of course a multi-parameter model, and there is a lot of freedom in it. And so, for instance, this is I've seen that already. Water, mantle temperature. There are alternative scenarios. We can increase the effect of the continent. We get then a two-stage development that we're not really seeing in the Earth. Or here we use some of these ideas, that the exponent to the Rayleigh number should be smaller, and then we see that we can delay the formation of continents, because in our model the continents form actually too early. So we can delay that to more reasonable times and get to here. And this is temperature and viscosity and so forth. So, yeah, this is an old model by Armstrong. Well, maybe there's still something to it in the Taylor and McLennan model. Now our model would actually more fit to this thing here, but we can think that we can actually construct models that are closer to that thing here and represent that. You see that, there may be, we have a relatively small difference in the two, in our standard model, in the biotic and the abiotic world, but they can be much more significant depending on parameter values. Anyway, I'm arriving at my conclusions for this part. So terrestrial planets are heat engines, converting thermal energy into mechanical work and magnetic field energy. Planets differentiate into chemical distinct layers according to their densities. But at least for the core, they probably do that contemporaneously with accretion. The heat engine is driven by thermal and compositional convection. I don't know what that C here means. The vigor of mantle convection is regulated by the temperature and the volatile concentration dependence of mantle viscosity. The strong dependencies, in particular for the temperature, result in convection modes such as stagnant lid and mobile lid convection, or this thing being equivalent in a way to plate tectonics. Same here. Temperature and volatile concentration dependencies set up important feedback cycles that may include life. I'm not saying that is necessarily so, but we used, a proxy, a geological proxy, sedimentation rate to, include the effects of life. There are others, like, life acting as catalyst in water storing reactions, like the illite-smectite transition, and the formation and evolution of continents and the short circuiting of chemical cycles may be the most important feature of plate tectonic serving habitability, along with the renewal of nutritions. And this may, the evolution of continents may, in a way, depend on the biosphere. And I should note at this point that this is different, but of course from thought point of view, similar to what Francis and together with Monique Rosing and others have proposed in 2006, where you said that the continents are there because of the photosynthesis, we've tried to put in here a model that was a little bit more tied to effects of more direct effects perhaps, but in a way, it emphasizes the importance of continents and the possible feedback of life on continents in a way similar to what you guys did back then. I should say that I profited from these people here, and I would put some perspectives out there. So go ahead and study the Earth-like planets and satellites in the solar system to find out how these guys work. Study asteroids, comets, exoplanet systems, to study solar systems and planetary systems. Address the habitability of planets. This is why you're here, to find, is life a universal phenomenon or is ours a rare Earth? So working together, planetary science, solar system science, astrobiology, and so forth. And I just got this recently by Jean Raymond from the internet, and he proposes a better solar system. So maybe I'm leaving you with that. And thank you very much for your attention.